Hi, we have a neat curve here. We've got the fact that it's got sine x in it, so it's kind of going up and down and up and down and so on. And the multiplied by e to the minus x means that over time it is going to be heading towards 0. We're asked to find the coordinates of p, q, and r. That is essentially the first three positive roots. So let's go ahead and have a go at that. It's going to be that e to the minus x sine x must equal 0. For this to be the case, and e to the minus x is never 0, so that just gives us that sine x is 0. And if we do a little sketch of sine x, it looks like that. So we've already discounted 0, so it must be that we get, it's just going to be pi, 2 pi, and then 3 pi. It did ask for the coordinates, so I just write that p is pi 0, q is 2 pi 0, and r is 3 pi 0. Okay, good start. We're then asked to use integration by parts to show that this integral is equal to this. All right, let's do this. By the way, there's a lot more to this question. Okay, integration by parts. So I'm going to call this one u and this one v dash. I'll probably get away with doing it the other way around. So u dash is going to be minus e to the minus x, and v is going to be minus cos x. So remember, integration by parts is uv minus the integral of u dash v dx. So minus e to the minus x cos x minus e to the minus x. So that I'm going to cancel that out. Oh, then I've got another one. So actually, sorry, there's a triple negative, which leads me back to a negative here. All right, this is all well and good. Actually, how do we integrate this? Well, you might be able to see that if we do integration by parts on this again, we're going to somehow get back to this, which I'm going to call I at this point, capital I. So let me call this u now, and this v dash. Okay, I'm gonna leave that negative for the moment. I just want to get a nice result for this. So uv minus the integral of u dash. So minus, so this becomes a plus, and then v, so we don't get a triple negative this time, just a double negative. Therefore, I is equal to this minus e to the minus x cos x. Then I need to minus all the rest of it, e to the minus x sine x, plus this same integral, so it's an I here. Now if I deal with this bracket, I'm going to get a minus I, so I can then add it on to the original integral, 2I, and I'm going to be left with minus e to the minus x cos x plus sine x. And I forgot a constant, sorry, when I integrated, there is going to be I kind of can't forget about it. You can forget about it in some places because you still have to do an integral, but the fact that I'm now moved the integral over means I needed to bring this constant in. So finally, this thing here is going to be, now I need to, yeah, that's all well and good. So I can basically divide by 2. Okay, in brackets we've got the sine x and the cos x, and then plus the constant. So we've done this. Okay, good job. As you can see, we're like on this question 7, there's already, this is just part B, 5 marks. There's already quite a lot to do to get to that. Let's see, it's going to be useful in a minute, I'm sure. The next part says that the terms of a sequence represent areas between C and the x-axis for successive portions of C where y is positive. And A1 and A2 are shown in figure 3. So we can see A1 here between 0 and pi, and we can see A2 between Q and R. And we're not interested in this negative part. And then we're being asked to write down an expression for AN in terms of n and pi. All right, I might need to copy this question. To be fair, this is going to be a long page. So first things first, let's write down what A1 is equal to. And that was the integral from 0 to pi. And then A2, we didn't include pi to 2 pi because that gave us a negative sort of part. So it's going to be 2 pi to 3 pi. And that means if we sort of extend this, we can see that AN, or every time we're going along, like we're skipping out a pi, just need to think about this. So we've got 0 to pi, we've then got 2 pi to 3 pi, then it would be 4 pi to 5 pi, and so on. Now n, the smallest that it's going to be, gave us 1. So like your first protocol might be, hey, it's going to be 2n pi, but no, because n is 1 to start with. So it can't be that. So it's going to be 2n pi minus 2 pi. So 2n minus 2 pi. That will work. So when n is 1, we get 0. When n is 2, we get 2 pi. When n is 3, we get 4 pi. This works. And then we just need to add a pi to this, which will give us 2n minus 1 pi. And we're done. Well, we're not done, but we've got a general expression. Now, we know from before that this gives this, so we can evaluate it. It was minus a half e to the minus x sine x plus cos x There we go. Substitute the limits in. minus minus. Okay, now let's think about this. We know that sine of n pi, where n is an integer, is always 0. So this is actually going to go, as is that one. Cos is a little bit trickier because cos pi, okay, if we just draw cos of pi is minus 1, but cos of 2 pi is equal to 1. So basically, if cos, I want to write an even, cos of m pi is equal to 1, where m is even. And cos of, if we did m plus 1 pi, then that would equal minus 1. So therefore, the an, I've forgotten that's what we're trying to find, an is going to be minus a half. It's a bit fiddly. Minus a half e to the minus 2n minus 1 pi. Now this here will always be odd because 2n is even, so 2n minus 1 is odd, and therefore that will give us minus 1. So we'll get a minus 1 coming from here, and then we're going to add, because there's a double negative, and then this term will necessarily be even. So an will equal, I can factorize the half out. There's a double negative here, minus 1 and a minus. So it's going to be e to the minus 2n minus 1 pi plus e to the minus 2n minus 2 pi. And I'm just going to leave it like that for the time being. Let's just recap. We have, we've got the areas underneath a curve. We're just interested in these positive ones. The curve itself is e to the minus x sine x. We integrated it and got this result. We then looked at these positive areas and actually calculated what they were, the general nth term for it. And now we're on part D. So we're being asked to show that when we add all these areas together, we actually get a geometric series. And we're going to sum it to infinity. So we can write down that it's going to be the sum from n equals 1 to infinity of this thing here. I think it makes sense to probably try and expand this out a little bit, so that this is going to be e to the minus 2n pi and then plus pi, and this bit here is e to the minus 2n pi plus 2 pi, and this can be rewritten as e to the pi times e to the minus 2n pi, whilst this one is e to the 2 pi e to the minus 2n pi So we can actually take the half out, and we can factorize. Actually, I don't want to rush this. So n equals 1 to infinity. I can write e to the minus 2n pi e to the pi plus e to the 2 pi. I've factorized this common term out. And then this is just a constant. It doesn't depend on n. So we can bring it outside the summation. And technically, this is actually minus 2 pi to the power of n. So every time we are timesing by another e to the minus 2 pi, this is a geometric series. It might actually be easiest to write the first few terms out. So it'd be e to the minus 2 pi. When I'm just going to go back to here. When I substitute 1 in, then e to the minus 4 pi, 6 pi, and so on. So consider I'll just forget about this for the moment. We've got that the first term is e to the minus 2 pi, and what are we timesing by every time? We're also timesing by e to the minus 2 pi. And the sum to infinity is therefore a over 1 minus r So is that looking all right? Is that the sort of thing we want in the final answer? We've got this. Now remember, we still need to times by this purple bit here. It's always worth just having the actual answer on hand. So it's a half e to the pi plus e to the 2 pi, and then you're timesing by this. So first things first, let's bring it all together. And I'm going to times this part by this, so that will leave me e to the minus pi plus 1 all over 2, 1 minus e to the minus 2 pi. This next bit is the trickiest bit, I think, because it doesn't quite look like it's in the right form, but actually these two things are the same. It's just that we have an e to the minus 2 pi, and actually this is a strange case of a difference of two squares. This is 1 minus e to the minus pi multiplied by 1 plus e to the minus pi. Just sort of throwing that out of nowhere, but this is in the form 1 minus x squared. It's just that x is equal to e to the minus pi. So we get 1 plus e to the minus pi, 1 minus e to the minus pi. And this is brilliant because these two cancel. So we got 1 over 2 1 minus e to the minus pi. And if we multiply top and bottom by e to the pi, then we need to times both of these two terms, so we'll get e to the pi, and then this gives us minus 1. Whew, what a fantastic result. Tough, I think, this bit here. The last part of this question, all the way back up here, asks us to find the exact value of this integral, i.e. all of the curves added together, ignoring the negative parts. We are fortunately told that if you find the whole integral, then you would get a half. So we have the positive areas minus the negative areas, because that is what is actually would happen. If you find the whole integral, you would be adding these parts and minusing these parts. Now we also know that the positive areas are equal to e to the pi, and this is from just above. And therefore, the negative areas will equal this minus a half. We can get this over a common denominator. So it's going to become minus e to the pi minus 1. Which will leave us just with 1. Because these two will cancel, and we're just left with it. We've got this double negative, so we'll get this. So finally, if we took the modulus of the function, i.e. this goes up here and becomes positive and so on, then it's going to be that result from before plus this negative 1 . And therefore, our final answer is going to be e to the pi plus 1 all over 2 e to the pi minus 1. Brilliant. Well done.